The part of chemistry that studies rate of chemical reactions. And when you see rate of chemical reactions, let's see rate of chemical reaction. We're talking about the pace at which the products are getting formed or the reactants are getting used up. It's a two-way thing. When you have the reaction A plus B, to give you C plus D, reversible reaction like this. The rate at which A plus B is forming or combining instead to form C and D is what we call the rate. So you can also say that means rate of reaction just has to do with the pace at which C and D is getting formed, or the pace at which A plus B is getting what used up. So when we now want to specifically now concentrate our mind on this definition in terms of concentration, we are talking about the fact that we're doing the reaction. As time goes on during the process of the reaction, what will be happening to this C and D? What will be happening to C and D? You are watching me like a movie. Think about it. C and D what? The concentration of C and D will be increasing now because it will be forming A and B will be forming C and D. So the concentration of C and D will increasing. Why the concentration of this will decreasing a bit? So in this one, what we're just saying is that the rate of reaction is just the rate at which the concentration of either the product and the reactant are changing with what time. You get what I'm saying? So that's how you can say the rate of reaction is what is the change the concentration of product over what change in time, which is still equals to the what change in concentration of reactant over what change in time. And there is always a negative here because the reactants will get what used up. You get what I'm saying? Because the reactants will be getting used up. Okay, because of the fact that there's a revision stuff, I'm not going to be really talking about some non-important concepts. So from here, I will just talk about this. I want to quickly talk about molecularity and order of reaction. Molecularity and order of a reaction. When we hear the word molecularity, we are talking about what's the number of what? Of moles of the what? Of the reactants that are present in that reaction. So in your molecularity only depends on the what? On the number of what? The number of moles. And the number of moles of the what? Reactants. Because it's not focusing itself on the mole, the product. So when you have something like this now, 2A plus B to form D. You have a reaction like this, you now have another one, A plus B to form C plus D, in the two moles of C. Then maybe you now have 2B to form D plus 3D. Then you now have another one, maybe a dissociation reaction like F to form C plus A. Now each of these reactions have different molecularities. And I said the number of moles of the reactant present in that reaction will determine the molecularity of that reaction. For example, now, if I should give, okay, so people are connected. If you are connected watching the video, there's no problem. You just drop your comments in your question on the comment section there. So when you have 2A plus B to give you D, you count the number of moles that you have at the product side, at the reactant side, and that tells you the molecularity of the reaction that you have. Okay, good. Now we have 2 moles of A. I get it now. 2 moles of A. 2 moles of A reacting to form 2 moles of A plus B reacting to form D. Now the total number of moles on the reactant here is 3. 3 of A and 1 of B. So that tells us that it's 10 molecular. Now we have 3 types of molecularity. We have the unimolecular. 10 molecular.
Yeah.
TR molecular, 10 molecular. Now, we have three types of molecularity. We have those that are unimolecular, that means one in which the molecularity is one molecularity. Then we have bimolecular. Those are the ones that their molecularity is two. Then we have molecular, three and above. It's not trimolecular, it's not tetramolecular, it's nothing like that. So anything three from above three is what? Molecular. So molecular, that's three molecular and above. So I'm saying any molecularity greater than three is molecular. Let's now look at this. It means that if we are giving a question like this about two to state the molecularity of these reactions, it means this first one here is going to be 10 molecular, but you have 2 plus 1 mole of B, which is the reactant. Remember, we choose the reactant fully. In the option, you will see tetramolecular for those people that are not informed enough. So I know that your product is not going to be part of it. So this one now, it means it is what? 10 molecular. And why?
Because it has three.
Because that does?
3 moles.
Because that's 3 moles. I get it now. What about this one? How many molecularity? 5 molecular. So you have 1 mole here and 1 mole here, which is 2 altogether. So this is bimolecular. Then this one, what is this one going to be? This is also bimolecular. You have just 2 moles of B, which is the reactant at the reactant side. So this is also bimolecular. And this last one is the unitary dissociation, where you have one reactant, so that is what? Unimolecular. So the molecularity is unimolecular. That summarizes everything about molecularity. Now I want to talk about the order of the reaction. Order of reaction, I want to check where the camera can see. I don't write where the they're looking at me like one comment to do. Okay, so order of the reaction now. When we say order of the reaction, the order of the reaction just has to do with the exponent to which the reactants are raised, or should I use the word, the exponent of the reactants in a given rate law expression. That's exactly what we call the order of reaction. Or you say the power to which the reactants are raised to in a rate reaction or rate expression or rate law, any of them. So I'm just saying right now that your order of reaction is the exponent of the reactant in a given rate law expression. And the rate law, when they actually state the rate law just says that the concentration of the rate of your reaction is directly proportional to the concentration of the reactant. I get it now. The rate law is stating that the rate of a reaction, which is R, which we call the initial rate, is directly proportional to the what? To the concentration of your reactant. That's what rate law states. And from that, now we can now see from our rate law, that I just stated now, from the rate law, which states that,
write it down.
Yes. Which states that the rate of a reaction R, the rate of a reaction R, which states that the rate of a reaction R is directly proportional to the concentration product of the reactant in exponent of their order. in exponent of their order. Mathematically now, what are we trying to say? To the concentration product. Thank you. Of the reactants in exponent of their orders. Now, for those of us now that have written that, what does that imply? The implication of that right now is that we'll be having an expression like this. It means our original expression is given as this. R is directly proportional to concentration of reactants. Of course, I believe you know that this enter into this kind of bracket, it means the concentration of the reactant raised to the power of an exponent A. Now, this A that is exponent is the order of the reaction. Order of the reactant. Are you getting me now? Because we have order of reaction and the order of a particular reactant. A here is the order of this reactant. Are you getting me now? But the sum of all the orders of the reacting species, the sum of all the orders of the reacting species is what we call what? The order of the reaction. Now, but let's bring in our K to remove this. So we have R is equals to K. You know your variation, anytime you have to bring in, remove the proportionality sign, you have to bring your constant. And right here, our K is the rate constant. Is the rate constant. Our K is the rate constant. Okay, now look at something. Imagine you have the original expression like this. R equals to K A B. It means that your order of your reaction. Now let me explain something. It means A, this small letter A here, is the order of this reactant species here, A. You must be able to differentiate when they are asking you for the order of reaction or the order of a particular reactant species. In some question, they will not ask you to find the order of the reaction. They just tell you what is the order of this reacting species. They just tell you what is the order of this reacting species. So they expect you to know that okay, the order of the reacting species is order for that reactants. So they say overall order now. The order of the reaction is going to be what? The sum of the order of each species. So we have what? A plus B. That's also order of reaction is going to be. So that does it. Now, aside from that now, let's now move further. We've been able to look into this. I'll now go straight to the types of Brace law that we have. But before I start writing the types of Brace law, I'll just use my mouth I'll just vocally mention the factors affecting the rate of a reaction. So the major factors affecting the rate of a reaction is temperature, of course. The higher the temperature, the higher the rate of the reaction. Also, the pressure also affects the rate of the reaction. Your concentration affects the rate of the reaction. The nature of the material, the surface area, catalyst, which is the very important aspect that affects the rate of the reaction. The catalyst, all those affect the rate of the chemical reaction. Those are things you can just read off. These are revision stuff. You can just check them off. You can actually mention 5 factors affecting the rate of reaction and explain any 3 or explain all of them. You get which is going to get. Now, the type of reaction, we have the differential rate law. And when we say differential rate law, what does it mean? Anybody? A differential rate law is the rate law that shows you the relationship between what and what? Between rate and concentration. Are you getting me? Between rate and what?
Concentration.
Like this expression here is a differential rate law. It's showing you the relation between the rate and what? Concentration. Yes. Of the reactants. It shows the relationship. As soon as it's written.
Use exponent instead of sum of exponent.
Yeah.
Order of reaction.
Sum of exponent of the reactants. Then sum of exponent. I said it vocally already, so you should know. Okay. It shows the relationship between what? Between the constant and the initial rate of the reaction and the concentration of the reactant. The reactant. That's that for that. And that's exactly how we write the initial and differential rate law right here. The second one is the integral rate law, which is a very important aspect. Integral rate law shows the relationship between what and what. Good. So integral rate law shows the relationships between the concentration of the reactant and the time. So both of them are very important anyways. As you can see, one will be helping us to know how the concentration is changing with time. The second one is helping us to know how the rate is changing the concentration. Okay, so we have three types of, from in the integral rate law, we have three different orders. Are you getting me now? Specifically, we have three. We have the zero order reaction, we have the first order reaction, and the second order reaction. And each of them have their integral rate law formula. But before I move on, I will specifically want to tell you something about from your differential rate law, one thing they can ask you. Now, it is only when you say zero order, meaning that the overall order of the reaction is zero. So look at something. Imagine I have something here now, like R equals to A. If the order for A is zero, what will be A? That means A raised to the power of 0 will be 1, so we'll be having R equals to K. It means that it is only in your zero order reaction that your rate of reaction is equals to your rate constant. It's only in the zero order reaction that the rate of reaction is equal to the what? The rate constant. Okay, I said we have three different types of reaction order. We have the first order reaction. Now, your first order reaction, what's the formula? We have the natural log of what? Of your A naught equals to minus KT plus ln A. Then for the second order, you have 1 over A equal to KT plus 1 over A naught. Then for the zero order, you have A equals to minus KT plus A naught. I think it's written before. So that's after that. These are the three different. Now, if you look at the similarities there, this is A. The difference between this one and this one is just the link. And we use that to remember. This is link A equals to minus KT plus in A naught. While this one is A equals to minus KT plus A naught. Each of them like this can be related to your Y equals to mx plus C. That's your equation of a line. Y equals to mx plus C. Because they can actually ask you questions like that. This is Y equals to mx plus C, right? So let's imagine we want to take this first order reaction here and put here now under this equation in A equals to minus KT plus in A naught. Now it means that our y, if we plot a graph, it means that if we plot a graph, for those of you that have been coming for the practical, this will not be strange. If you plot a graph of in A naught on your y-axis and time on your x-axis, and you get a straight line, they can ask you when a graph of in A naught is plotted against time, a straight line was obtained. What order of reaction is given? You have to know that it must have been a first order reaction, because only first order reaction about if you have in A plot against time, that will give a straight line, because it's only the first order reaction that is written in A and C. So the gradient of that line is going to be your what? Your K, your rate constant. As you can see, this one shares with this one. I see it down. Then your intercept on the y-axis is going to be your in A naught. The same thing applies to each of them. So let's move on. The revision class. Anybody that has questions or you feel you need me to clear some things on this, you can come later and clear yourself. Now, each of these things have their half-life formula. Each of them have their half-life formula. And I don't think okay, let me just derive it there. This thing is beyond the scope. Did I derive it before for you? They only ask you to derive half-life, and you derive from here. So let's just do the derivation of the half-life for each of them, because you can actually get the half-life of first order reaction, second order reaction, and third order reaction from here. I'm going to be deriving one of them, and the mechanics in deriving one is how you're going to derive the remaining. Okay. Now, let's get it right. To derive half-life, half-life is written as half-life, you write half-life as T1/2. And that half-life means the time taken for half the concentration, half the initial concentration of the reactant to get used up. Time taken for what? Half the what? Is the time taken for half the concentration of the reactant to get used up. And based on what I had asked this before, for you to derive the half-life of a particular order of a reaction. So this is first order reaction now. Imagine thoughts for a first order reaction. Which is given as in A equals to minus KT plus in A naught. We know that this A here, this A that does not have naught on it, does not have zero on it, it means the final concentration of the final concentration of the what? Of the reactant after the whole process has taken place. But this A naught here means the initial. Now, from the statement I made about the half-life, it means that in an half-life process, the final amount that will remain will be the half of the former. So if since, or let me do what, after half-life, it means that after half-life, our final concentration is supposed to be equal to what? 1/2, that's half of the initial concentration, which is equal to this. 1 times this over 2. You get what I'm saying now? It means that after half-life, our A is equal to this equals to this. Are we getting what I'm saying now? Okay, good. Since you have been able to see this now, we can now execute this. So we're saying A is equal to A naught over 2. We can substitute it in this equation here. So when we see A, we put A naught over 2. So this equation is going to become, instead of A, since it's half-life, half the concentration are gone, you say A naught over 2 is equal to minus KT half, but the T now is half-life time that we're using. Since we have done half of the mass getting used, plus in A naught. What we're making the solution formula is this T half. So let's carry this one to this place. Or we can carry this one out and bring this one in. Anyone works. So let's carry this one out so that this minus should go away. Okay, let me carry this one out and bring this one in. So that will be KT half equals to in A naught minus in A naught over 2. That's what we'll be having, right? Okay, so what are we going to obtain? Dividing both sides through by K, we have over, or before then, let's simplify what we have here. Let's simplify. So we'll be having KT half, what are you doing? Are you following? KT half will now be equal to what? How do you operate with this in log? Minus in log turns to division, abi? So you say in open brackets, you know, this means log, operate to the log, like your log. So that was A naught, abi, divided by what? A naught over what? 2. You get what I'm saying? And if you want to turn this division to times, what will happen? If you want to make it times, it will be 2 over what? 2 over A naught. So A naught to cancel A naught. Abi? A naught to cancel A naught. And that will be giving us what? KT half. So you just joined. Abitaiwo, any of you, I'm still going to post it. Don't worry, I'll post it. I'm just preparing because I want to, I say I'm not feeling fine. So I'll just post it later. You see it from the beginning. So KT naught now because what? In what? In what? In 2, abi. So dividing both sides now by in 2, I can just do like this. Divide both sides by what? By K. So we can get our T half. We'll be obtaining what? Our T half because in 2 over K. That's the half-life for a first order reaction. And that means it will be equal to how many? In 2 is 0.693. All over what? K. So that's the formula for the half-life. Is it difficult? The same procedure is what you will use for the remaining orders. It's just for you to make use of their formula. As you're trying to get the half-life of a second order reaction, you'll be putting the formula for a second order reaction right here. You'll be putting the formula for a second order reaction right here. If you're doing for a zero order, you'll be putting the formula for a zero order here. Then this process here is what you will effect into it. The fact that for half-life, the final mass and final concentration should be equal to half of the initial concentration. You guys that are joining in, I already said, don't worry, I'm still going to post it anyways. Don't be scared. I'll still post it. Don't shout. So that's that one for that one now. That's that for that one. Now, there are 2 ways. We're almost there. But there are 2 ways for you to, to obtain the order of the reaction, because what they'll be asking you in your exam is write the what? The rate law. Write the rate law. What is the rate order? What is the overall order? What is the order of this species? I get what I'm saying now. So you can get it in 2 ways. We have the experimental process and from the what? And from the what? From the elementary steps.
Oh, yeah, that's okay.
Yes, from the experimental process and from the elementary steps. So let's take it one after the other right now. I'll start from the first one and we'll solve the question. From experimental data and from elementary steps. I'm going to explain the elementary step with one example and I'll move on. But before then, I want to tell you something about the units for your K. Because the unit for a K for your rate constant is not the same for every order of reaction. I get it now. The unit of your K for a first order reaction is different from the unit of your K for a second order reaction and so on like that. And let us now find out. Now, the rate of a reaction R, listen up. The rate of a reaction R has the units m per t, or per second rather, sorry. M per second. That's the unit for R. I get it now. And we know that R is equals to K concentration of reactants raised to the power of an order. Let's imagine that order was a second order reaction. Let's find our K, the unit for our K. So that means our K will be equal to R all over reactants raised to the power of 2. And we know that this box here means concentration, which is M. So that means I'm saying what do you need for M for R? Mass per second divided by this one raised to the power of 2, which is M raised to the power of 2. I told you this concentration, that's molarity. And this expression is the same thing as M all over S times 1 all over M to retain this into times. So M here 1, M here M. So what will be the unit? The unit will now become M per 1, S per 1. That's the unit for a second order reaction. If we're dealing for a first order reaction now, maybe R, if it was a first order reaction, we're having K equals to R all over reactants raised to power how many? 1, So that means the unit will be M all over S, which is R. K. The reactant will be how many? Divided by M, which is the same thing as times what? 1 over M. M will cancel M, so our unit will what? Per second. Now let me just give you this hint. It means that as you are going down like that, that's how the trend goes. For a second order reaction, it's M per 1. For a first order reaction, it's M0. If there to be a third order reaction, M per 2. For a second order reaction, M per 1, S per 1. But if there to be a third order reaction, it will be third order will be per 2 per second. That is third order. If there to be a third order, you'll be having M per 2 per second. If there to be a fourth order, you'll be having M per 3 per second. If there, like when we add first order, when we add a first order, we add per second. If there to be a zero order, you know this M was 0, that's why we have per second. It's not what? M per second. You now have like that. That's it. That's the trend. But sometimes in your professional exams, they will not be using N to represent it. Now let me show you another way they can use. They'll be using mole per liter. They'll be using mole per liter. And when they're using mole per liter, what does it mean? The thing is, you know that this N here, molarity, this molarity here, molarity is still the same thing as mole over volume. That which is mole per liter. I get what I'm saying. Yeah. So let's substitute now. We know K is equal to R over what? Concentration, concentration of reactant per 2 for a second order reaction. So what will it be? You'll be having what? Mole over L, which is our R, per what? Per second. Mole over R per second. And after this, divided all of them. Because we know that this is M per second, and this M mole over L to per second, time over second, and that goes L times S down. Divided by, let me write it like this, you're having mole over L by S, which is this one, divided by reactant square. And reactant, that's concentration, which is this. I say anytime you want to use this, which is this. And that means you'll be having mole divided by mole over liter square, which is square. You understand? Square. Now, let us now turn this into times. It will become what? You'll be having mole over liter per second times liter square over mole square. 1 mole will cancel 1 mole, will be left with 1 mole. 1 liter will cancel 1 liter, will be left with air. So what will now be the unit? The unit will now be what? The what? Liters per mole dot second. liter per mole per second. That was what we did for a second order reaction. Now this is follow the same trend that we're doing. It's still the same thing as per m because n by m mole is per m. Ordinary m is mole over n, that is mole over liter. Since you're not saying per, that is raised power minus 1, you have to swap them. So it's still the same what I did before. You understand? For more explanation, you can just meet me, contact me. I will explain to you. So let's now talk about from experimental process. Obtaining order of reaction from experimental process. So I might just call me a question from there. Want to solve one question from experimental process? Now, from the one for experimental process, they will give you a table. I get it now. They will give you a table, and they will tell you from that table that you should obtain the find the rate constant, find the order of the reaction, write the rate law, stuff like that from the table. That's what we mean from experimental data. Okay, let's see.
NH4 minus.
Did that actually started? I'm just giving that NH I was giving.
No, started.
Oh yeah, NH4.
Should I give you another one?
I don't know, just
NH4 minus.
now given this question, NH4 minus
Q equals
AQ
plus NO2 minus
plus NO2 minus this is plus. Ammonia can minus AQ
okay, NO2 minus. Then the reactor, the product N2 gas
N2 gas
plus 2H2O.
You know, anytime we're dealing with rate of reaction and rate law, we only depend on our reactant side. So we know this will depend, but because we're getting from experimental data, you see what we do here.
Determine the rate law.
Determine the rate law. Determine the rate law. And I told you to write the rate law, you have to express it in this format. To write the rate law, you have to express it in this format. R equals to K, the first reactant, which is the power of the order of the first reactant, the second reactant, which is the power of the order of the second reactant. That's how we want to express it. That's the rate law. Yes?
The order of reaction.
Determine the rate law.
And second, the order of reaction.
Is the order of reaction.
Find the rate constant.
Find the rate constant. So now, that's not all. Where's the table?
This table, the experiment.
Put it accordingly. Experiment. So we have on the table, they gave us the table, they wrote experiment. They wrote NH4, I mean,
Yes.
concentration of NH4. They wrote concentration of NO2.
Initial rate.
They wrote initial rate.
First one.
They give us values. The first value was what?
0.100
0.100
M.
Okay, the unit is in molarity. Yeah, I'm going down. Right, let's go like this. Let's go like this.
0.005
0.005
M.
M.
1.
Did they give us the unit for the initial rate?
1.35 minus 7.
And 10 power minus 7.
Yes. 0.100 M.
We know our initial rate actually is going to be in molarity per second. Our initial rate is in molarity per second. What did you give us here?
0.100 M.
0.100 M.
0.010
0.1010 M.
2.70
2.70 times 10 power minus
7.
yes.
0.200 M.
0.200 M.
0.010 M.
0.010 M. It's 5.4 times 10 power what?
minus 20.
Do you three things, Abi? Good. Now, they want us from this table. If you want more question on this later, we can come. Later, I have problems enough. They want us from this table get these other things: rate laws, order reaction, and rate constant. Now, to get the rate law, I've told you already that we need our orders of reaction. So we see, you start from the first one. For our NH4 plus, when this 2 o'clock in formula. For our NH4 plus, you will have to check. To get for your NH4 plus, you have to check where your NH4 is changing, the values are changing, that this place, your NH2 is constant. And it does not have to be in the exactly the same. It can be from the first experiment to the third experiment that is in, or from the first experiment to the fifth experiment, notwithstanding. So for your NH4, if you look at it, my NH4 is changing from year to year. It's changing from year to year, Abi, but it is not, it is constant along here. And that's exactly what you need. But it doesn't change from number 1 to this place. It changes from 0.1 to 0.2. But I cannot use from year to year. Why? Because it is not constant along year to year for NO2, the second reactant. That's why this is the correct place for my NH4. So I will now write, you now write it there for your NH4. I will advise you, you can do it anyhow, but I will advise you do biggest divided by smallest, so you don't have problems with your divisions. So 0.2 is bigger. I'll just write 0.200 divided by 0.100. That's the second one. 0.200 divided by this one. Raised to the power of x. So x is what we're looking for. That's the order. That's the order for NH4. Nothing is equals to, you pick these two. So these are the exact two you go and pick in your initial rate. Some questions, let's put the initial rate first. In as well the label it, you trace it to your initial rate. That's the two we used. So you did experiment 3 divided by experiment 1. It's the same thing you must do here. That means this one here divided by what you have here. Okay, this light is like it is actually shining bright on this stuff. So anyways, I'll call the value out. Just listen. We are having what here? 5.4 times 10 to the power minus 7 divided by 2.70 times 10 to the power minus 7. You understand? So it is this value we are looking for here. When you divide this, what do you get? You get 2. You get 2. You'll be having 2 raised to the power of x is equals to. When you divide this 2, you also get 2. And that means 2. You get it? So we know this 2 is 2 to the power of 1 anyways. So 2 can cancel 2. So our x is equal to 1. It means the order for NH4 is what? Is 1. Do you understand? It is a first order, like the reactant is the first order reactant. Now, not the reaction, the reactant. So let's now do for the second one. For your NO2, where your NO2 changing, that the remaining is not changing. You say check now, NO2 is changing from year to year, and this constant in this NH4 from year to year. You understand? So we are going to use this place and this place because along this place is changing for NO2 and constant for this. Do you get it now? So you use it like that. And I told you it's better if you get divided by smallest value. So that would be 0.01 divided by 0.005 equals to what? This one divided by this one. Because we use this one divided by this one first, we must do the same thing here. So we're having 0.010 divided by 0.005. This power of y. That y is the order we're looking for. Equals to just the same way we did this one. 2.70 times 10 to the power minus 7 divided by 1.35 times 10 to the power minus 7. So when you divide this, you get 2. Equals to, when you divide it, you also get 2. So our y is equal to how many?
1.
So that means our order for this one is also what? 1. So let us now write our rate law. Our rate law will now be what? That is our answer. R equals to what? K. I see that now. Into brackets. What's our first one?
N
is for rate power how many?
1.
1. Then what's the next one?
NO2
Rate power how many?
1.
Rate power 1. Because we got 1 for the NH4, y, and 1 for the round. So we can actually leave it without the 1. When you just tell it there, it shows that there is 1 there. So these are answer. This is our rate law. The now says state the order of the reaction. And I told you the order of the reaction is just the sum of the spreadsheet orders like this. The sum of the exponents, which is the sum of the power. So what would that give us here? Eh? Okay. What does it give us now? It means that we'll be having our order reaction will be equal to how many?
1 plus 1.
1 plus 1, which is what?
2.
2.
That's second order.
So the reaction is the second order reaction. So look at it now. We'll be having as for the second part, order of reaction will be equal to 1 plus 1. That is the order of NH4 plus the order of NH2 is equal to what? 2. So it means it is a second order reaction. Since this is a second order reaction, I'm actually clear. Now what's the next one? Find the rate constant. So obtain your rate constant. This is what you just do. To obtain the rate constant, you will go along any channel of your choice and pick the values. Slot any channel of your choice. You can use experiment 1 values or this one or this one. Slot those values into your rate expression, which you've obtained here. I get it now. So if I want to use this first one, I'll put my average, my initial rate 1.35 this year. I will now equals to K. I'll put the remaining things, then we'll be making K the subject of formula, and that's what I want to do. So I'll be using experiment 1 value. You there that you have given, any of you can use experiment 2, 3. You see, you obtain the same value for K, if not very close. So, what does that imply now? It implies that since our R is equal to K from what you have gotten, NH4 plus NO2 minus. So I said I was doing my first experiment, Abby. So I think you guys have written it down there. So our R in the first experiment, initial rate was what? 1.35 times 10 to the power what? And 7 equals to K. What's our NH at that point? 0.1. And our NO was 0.05. Okay. And we know that these units, maybe I should write that as I'm solving, I should be writing the units. Then writing the units.
Unit of
each of them. So R, that is 1.35 times 10 to the power minus 7 units is what? Molarity per second. I told you that's the unit of our R. Or you see mole per liter per second. But here, they gave just a mole and molarity per second. Equal to K times, this is concentration, which is 0.1 molarity. Times this one now is concentration also, which was 0.05 molarity. So by finding K will now be equal to divide both sides by all this, because 1.35 times 10 to the power minus 7 molarity per second divided by 0.1 molarity times 0.005 molarity. And that will be giving us how many? What will be the value? We know that this molarity will cancel molarity here, we will be left with per molarity. So what will be the value? Let me do it.
we multiply the down. They give us
Everything together give us everything.
The rate constant and this unit will be M.
Yes, the rate constant unit will be M per 1,
S
S per 1. I've already said before. times 10 to the power of minus 4, and that's per n per second. So we are done with that question. That's how to solve questions from experimental mystery.
This thing I didn't do that.
No, general. No,
And
it's for biology. I will say it to one. So that's for that. I think that's exactly where we're going to stop for today. We're going to continue.
You send questions.
Yeah, yes. So I will send we'll continue from this aspect in our next chemistry video. Understand? So you guys should make sure you stay tuned
I'll just
and read.